So let's look at this problem. So again, we're starting where we left off on Wednesday by doing dimensional analysis to solve unit conversion kinds of problems. The question here in this case is about speed limit in particular. Stretch of land between Denver, Colorado and Kansas City, Missouri is 75 miles an hour. That's the speed limit for most of that distance. Question is, if you go 75 miles an hour the entire time and you don't stop and you don't slow down around cities or speed up over the prairie, how long will it take to travel the 604.9 miles between Denver and Kansas City? Now, the question here that we're trying to get after, we need to convert 604.9 miles into a time in hours. So we're turning a unit of distance into a unit of time. That conversion table that I gave you really does us no good in this particular case. But we do have another measured value that we can use. This 75 miles per hour is a conversion unit because what it is telling you is that when you're traveling at this speed, a distance of 75 miles is equal to 1 hour of travel time. And so if we have this idea and this conversion in place, remember, anything that we can hold together with equal signs, we can turn into a fraction of some kind. I have my 604.9 miles. I multiply that by my conversion factor. Since miles is in the numerator here, I need miles in the denominator there. And hours will go up top. The conversion factor says 1 hour is equal to 75 miles. And so if I carry out that calculation, my miles cancel out, and my answer, 604.9 divided by 75, carried out to 4 digits, because that's how many digits were here, is 8.065 hours. So it'll take roughly just a little bit more than 8 hours if you travel continuously. Now, chances are pretty good that you're not going to be able to travel continuously. Very few fuel tanks are able to go 605 miles without stopping, even with the best fuel economy. In an 8-hour drive, you're probably going to want to stop to go to the bathroom or to get something to eat. And chances are pretty good that you're not going to be able to stay 75 miles an hour the whole way. But assuming all of those things were irrelevant, that is how long it would take. Let's do another practice problem. This one about fuel economy. Fuel economy tells us the distance that a car can go on a set amount of fuel. One current model has a rating of 41.7 miles per gallon. What would that be in kilometers per liter? So in this case, we have miles per gallon. The key word here, the word per, indicates that we have a fraction. So I have miles over gallons here. And I want to convert the miles into kilometers. I want to convert the gallons into liters. And so both of these conversions are of the same kind. Miles is a unit of distance. Kilometers is a unit of distance. So I need a conversion of distance. Gallons and liters are both measurements of volume. So I just need a conversion that equates the two of them together. And so I'm going to go to my conversion table. And I'm going to see that, okay, 1 kilometer is equal to 0.6214 miles. That's the conversion here on the bottom. Now you could also use the 1 mile is equal to 1.609 kilometers. That would work just fine as well. The other conversion that we're interested in, gallons and liters, is right there. 1 gallon is equal to 3.785 liters. So now that I have those conversions in place, I can go ahead and try to solve the problem. So I have 41.7 miles per gallon. So 41.7 miles over 1 gallon. My first task is to convert the miles into kilometers. So I need miles in the denominator since it's already in the numerator here. Kilometers up top. Excuse me. 1 kilometer for every 0.6214 miles. My miles will cancel out. In the denominator, I've got gallons. So I need gallons in the numerator to cancel it out. Liters in the denominator. 1 gallon, 3.785 liters. Gallons will cancel out. I end up with kilometers in the numerator, liters in the denominator, which is exactly what I wanted. Remember, for multi-step dimensional analysis, I'm going to multiply by all of the numerators, divide by all the denominators. 41.7 times 1 times 1, divided by 1, divided by 0.6214, divided by 3.785. I had 3 digits coming in, so I'm going to have 3 coming out. 17.7 kilometers per liter. All right, any questions with either of those examples of conversions?
Are there more practice problems that we could do on our own?
I can find some. So let me write that down for myself. I will put some more practice problems in Blackboard. And you can kind of work through those. The homework that you're going to do will have a lot of these in it as well. So that'll certainly help you as also.
Thank you.
You're welcome. Okay. So we move now to density. Now, density is simply the amount of substance in a given volume. So we can find the density by taking the mass of a substance and dividing it by the substance's volume. And what's interesting about density is that every single substance has a density. And its density is somewhat unique to it. It helps us to identify what it is. So if I look at water, water has a very specific density at room temperature. And I can use that density to identify water from a series of other clear liquids that all look kind of the same. Now, what's also interesting about most substances is that because volume is able to expand and contract with temperature, those densities of substances will change, although slightly, they will change with temperature. And so most of the time, we talk about substances in terms of their kind of maximum density. So for water, water's maximum density is 1.00 grams per liter, or sorry, grams per milliliter. And that 1.00 grams per milliliter is actually measured at 4 degrees Celsius. So just slightly above the freezing point. As it warms up, it actually gets lower and lower in density, but the differences are pretty unnoticeable. 0.998, 0.996, 0.993. Relatively small amounts. So in general, we would say the density of water is 1 gram per milliliter. Now, closely related to density is something called specific gravity. Since a lot of our life, since a lot of our chemical reactions, since a lot of everything that we encounter is done in water, specific gravity gives us a way of comparing substances and their densities relative to that of water. So to find the specific gravity of a substance, we take the density of that substance and we divide it by the density of water. Again, for the most part, this density of water here is right around 1.00 grams per milliliter. So usually the density of a substance and the specific gravity of the substance are the same numerically. The main difference between them is that because I have grams per milliliter in the numerator and in the denominator, they cancel out. Specific gravity is a unitless measure. And where that's kind of important, kind of cool, is what we can do with specific gravities is we can use them to talk about how many more times dense they are than water. So for example, gold. Gold has a density just above 19. Its specific gravity is about 19. We would say that gold is 19 times more dense than water. A substance like isopropyl alcohol, I believe it has a density of about 0.79. So its density is 0.79 times that of water, or 79% of water. And so those little things can kind of help. And what they can also allow us to do is, if I have a large variety of substances, I can kind of see how they stack up against each other, so that if I saw that they were all together, I can make determinations about where they would be relative to each other in that vessel. Now for liquids, we often use a hydrometer as a means of measuring the specific gravity of a substance, in particular a liquid. Basically, a hydrometer is it kind of looks like a thermometer. It's a glass tube, but it's got a weight in the bottom. And that weight in the bottom is calibrated in such a way so that it will float a certain amount in the liquid relative to how water will go. And so what we can do is we can look at this and say, okay, based on where the meniscus touches the line, we can look at it and say, okay, if this line here is 0.6, and this line here is 0.7. The meniscus is between the two. Your book actually estimates that that puts it around 0.68, which means that this substance is about 68% of the density of water, which would put it right on par with a number of organic materials like heptane, hexane, pentane, and so on. So the hydrometer is a way that we very quickly can measure specific gravity of a substance. Now for gases have a similar kind of measurement called vapor density. So with gases, we usually measure density in grams per liter because gases are so much less dense than liquids and solids. And so if I looked at a particular gaseous substance like carbon monoxide or argon or helium, its vapor density would be taken by taking its density, whatever it is, and dividing it by the density of air, which is 1.29 grams per liter. And so when I do that division, what happens is that the value of that vapor density is going to tell us that where that gas is going to be relative to its container. So substances that have a vapor density that is greater than 1, those are substances that are heavier than air. And because they are heavier than air, they are going to tend to sink in whatever room or container that they are put into. Those with vapor densities greater than 1 are going to tend to be lighter than air, and they're going to have a tendency to rise into whatever room that they are in. And so this is probably the best explanation that we have for why helium behaves the way that it does. Why does a helium balloon, when we release it, go up into the sky? Well, because its density is considerably lower than that of the air. And so what is it going to do? It's just going to float up until it reaches a density that is similar to its own, or the dynamics of the upper atmosphere eventually cause the balloon to pop and release the helium up into the upper atmosphere. The last thing that we're going to talk about today is the concept and construct of matter. So now we're moving off of units and measurements, at least temporarily, and we're going to talk about matter. Now, matter, by definition, is anything that takes up space, that is, has a volume, and has a mass. So this is kind of our traditional definition of matter. Now again, mass and weight, so long as we are on planet Earth, tend to be interchangeable because the gravity on planet Earth is relatively constant and consistent regardless of where you are. The only time that we would really need to concern ourselves with mass in particular is if we were doing experimentation in a outer space scenario or a lower gravity scenario or another planet where gravity is going to be different than what it is here. So all matter possesses a mass. the way that we measure mass is by measuring the weight of a substance. Volume, on the other hand, refers to the actual amount of space. We've talked about volumetric units already. In particular, we look at things like liters, milliliters, cubic centimeters, which are the same thing as milliliters, or cubic meters if we're getting into larger quantities, and so on. When it comes to matter, we can describe matter as having a state or a phase. So another way of putting this are the phases of matter. So the three phases of matter are solid and liquid and gas. Now, there might be some of you that are up there going, oh, well, what about plasma? What about plasma? Isn't that the fourth state of matter? Well, yes, technically true. However, plasma refers primarily to ionized gases. We don't encounter a whole lot of those things. We either have to force their creation, or where we see it most often are things like stars and stellar objects. Not a whole lot of casual encounters with plasma. So we're not going to talk about it really at all in this class. The three states of matter are solids, liquids, and gases. Let's take a look at each of them individually. So with solids, solids are objects that have a definite volume and a definite shape. The definite volume comes from the fact that we have strong interactions between the molecules, and the molecules as a result are close together. The defined shape comes from the fact that those molecules are also ordered in their arrangement. And because they are close together. But mostly because of their order. So if I look at a solid from the molecular scale, what I should see is a very tight group of molecules that are arranged in a very orderly, very neat kind of fashion. There shouldn't be a whole lot of disorder. There shouldn't be a whole lot of disarray. They should be very ordered in their arrangement. Contrast that to the liquid. Liquids have definite volume, but they lack a definite shape. And so if you look at the words, again, definite volume, coming from the closeness and the strong interactions of the molecules relative to each other. But notice this time that we have disorder. And that disorder, notice how now the molecules are no longer lined up in those nice even rows. They're kind of a little bit more free-form. They're a little bit more on top of each other. That disorder costs the liquid its definite shape. Liquids do not have a defined shape as a result because they lack that order. So liquids and solids do have some things in common. Their defined volumes come from the close packing of their molecules together and the fact that their molecules have strong interactions with each other. Gases, on the other hand, have neither. So the gases that we're seeing here, we have molecules that are far apart, and do not interact. And as a result, they don't have a defined volume. And they don't have a defined shape either because of the disorder. So what we will find is that solids and liquids actually have a lot more in common with each other than they do with gases. Gases are kind of their own thing. And what we'll see is that we will actually study gases independently of liquids and solids because the gases and their properties are so different. Now, there's another way that we can classify. So that was called classification by phase or by state of matter. There's another way to classify. This gets into something called classification by composition. And when we do classification by composition, we are going to break our matter into two areas: pure substances and mixtures. Pure substances are considered pure because they do not vary in composition from sample to sample. So it doesn't matter if I have a sample of gold that is from Indiana and a sample of gold that's from Africa, or a sample of gold that is found in the Atlantic Ocean. If I go down to the atomic level, all of those gold atoms are going to look the same, or at least have the same characteristics in terms of what's in the nucleus. Same thing with compounds. Carbon dioxide is going to have one carbon and two oxygens, regardless of where it is found. Water is always going to be H2O. If I change it to something else, it's not going to be H2O anymore. So this idea of purity comes from the lack of variability in the composition. And so within pure substances, we have elements. Elements we can classify as having one type of atom only. So here's where our periodic table of elements is going to come in. We're going to talk about things like gold, silver, sulfur, germanium, carbon, nitrogen, oxygen, arsenic, tantalum. You know, pick your favorite element out of the 118 on the periodic table. All 118 of those elements have characteristics that make them their own. And we call them elements because every single one of the atoms in those samples has some kind of identifiable characteristic that we can pull. Compounds, on the other hand, kind of a longer definition here. We have two or more elements that are combined chemically in a fixed ratio. So in carbon dioxide, we had one carbon, two oxygens, that's CO2. Two different elements, but they're combined chemically, so they're bonded together. And the ratio is always one carbon to two oxygens. Sulfur trichloride, SCl3, one sulfur for three chlorines. Sodium carbonate, Na2CO3. Here I've got two sodiums 1 carbon, 3 oxygens to make up this particular compound. So I can make compounds that have more than 2 elements in them. Sodium carbonate actually has 3 in it. A lot of organic molecules can have, 4, 5, 6 different elements in them. And that's kind of on the low end. But the key here is that they do not vary in composition. Looking a little bit more closely, elements are substances that you cannot break down into simpler substances. And that's true physically as well as chemically. The only way I can break an element down into simpler substances is if I do some kind of a nuclear reaction with it, and that nuclear reaction is, well, going to destroy more than just the element itself. Overall, there are 118 known elements. However, just because there are 118 known elements doesn't mean that they're all present in the same amounts. Oxygen actually makes up about half of the mass of the Earth's crust. Oxygen is much more prominent than many other elements. Elements like silicon, carbon, actually are very, very common in the Earth's crust as well. And we arrange the elements on the periodic table of elements. More about that periodic table in a later chapter. Compounds. Compounds, again, 2 or more kinds of atoms in a fixed ratio. The technical term is a definite and constant proportion. Again, exactly what we've been talking about, a fixed ratio of one element to another. From a physical standpoint, we cannot break down a compound. Can't do it. I cannot simply boil water and get the hydrogen and the oxygen out of it. All that's going to happen is the water is going to go from a liquid to a gas. Chemically speaking, though, I can take that water, hook it up to some electrodes, and shock it, and the energy from that electrical shock will cause the hydrogen to dissociate and split off from the oxygen, and I will have separated it that way. That is considered a chemical process, however. And this brings us to our law of constant composition. Law of constant composition says that an elemental composition of a compound will always be the same, regardless of the amount that is present. So again, it doesn't matter how much we have. Yes, Joshua, that is called electrolysis when we shock it. And electrolysis is used in a lot of different kinds of chemical processes, not just for water. But with the law of constant composition, we are saying that regardless of how much we have, it doesn't matter if I have just the tiniest amount of water or the entire Atlantic Ocean. If I look at the water molecules that make up those samples, I will always find that they have the same elemental composition, 2 hydrogen atoms for every 1 oxygen atom. Mixtures make up the other kind of substance that we can classify by composition. Mixtures are physical combinations. And so the key word there is physical. They are combined physically, which means they can be separated physically. And each of the substances in that mixture retains its own chemical identity. So no chemical changes are taking place at all when a mixture is made. Now, in terms of classification of mixtures, we can classify mixtures in 2 ways. We can talk about mixtures as homogeneous or homogeneous solutions. Examples of these would be what happens when you dissolve salt into water, sugar into water, the air around you that you're breathing, sports drinks like Gatorade and Powerade. The thing that makes these kinds of solutions noticeable is their uniform appearance. They have a uniformity of appearance. So if I pick up that bottle of Gatorade, I'm not going to see all the individual components. It's going to look like one substance throughout. And so from that standpoint, homogeneous mixtures or solutions can be often confused for compounds because of that uniformity in their appearance. Heterogeneous mixtures, on the other hand, they lack a uniform appearance. You can clearly see the different components that are in each of them. Things like minerals. You ever get a good look at a piece of granite, you'll see all the little different kinds of stones that are in there. Get a scoop full of sand, you're going to see the silica, you're going to see little pebbles. You might see a seashell or two if you get it from the beach. Seawater. If I go up to the Atlantic Ocean and take a big old scoopful, I'm not going to just get the salt water. I'm going to get sand. I'm going to get kelp. I'm going to get seaweed. I'm going to get, phytoplankton. I'm going to get lots of little things in there, algae. And each one of those things are going to affect the appearance. So we're going to stop right there for today. On Monday, we will come back and review a little bit about classifications of matter. And then we'll get into talking about energy and temperature and some other kind of key attributes of science and chemistry in general. Any questions before we call it a week? All right, then I will see you on Monday, room 120 here on campus. Have a great weekend.